Okay, so let us quickly do a few problems. Let us quickly do a few problems, and then I'm going to end the session. Example: let us consider a linear transformation from the vector space R2 to vector space R3. Let us consider a linear transformation from vector space R2 to vector space R3. This is obviously a linear transformation because the V and W are different. Okay, so it is a linear transformation, and all the concepts which have been discussed in the previous session are only meant for linear transformation. It is not meant for any mapping, remember. And it is defined by T of a1 comma a2, a1 plus 3a2, 0, 2a1 minus 4a2. This is the way by which the transformation has been defined. Now I am going to find the matrix representation. My objective is to find T beta gamma. Okay, that is my objective to find. I was trying to capture a mosquito. Now solution. The basis, I always try to work with standard ordered basis. The basis of R2 is we know that it would be much better if we write standard ordered basis, because these theories have been generated for ordered basis, and it will be better so if we work with a standard ordered basis. So the standard ordered basis of R2 is beta is equal to 1 0 and 0 1. Okay, and the standard ordered basis of R3 is gamma is equal to 1 0 0 0 1 0 0 0 1. Okay, we know these things. Okay. First of all, I am going to apply this transformation and find out the image of these elements present in the standard ordered basis. So then what we get, if we apply the transformation on 1 0, the basis element TV1, try to recall TV1, what we get? We get 1 plus 3 into 0, 0, 2 into 1 minus 4 into 0, which is equal to 1 0 and 2, 1 0 and 2. And you know that this is nothing but equal to, if I want to express this in terms of W1 W2 W3, means this and that, the unique there would be unique scalars like 1 into, if I use a different color it would be much better, 1 into 1 0 0 plus 0 into 1 0 1 0 plus 2 into 0 0 1. Now we are applying the transformation on T01. So for T01 we'll get 0 plus 3 into 1 comma 0 comma 2 into 0 minus 4 into 1, and that would be 3 0 minus 4, and we will get, similarly we can express it as 3 into 1 0 0 plus 0 into 0 1 0 plus minus 4 into 0 0 1. Okay, so we have got it. Then your T beta gamma would be, try to apply the definition which we have learned in the earlier session. It would be what? Matrix 1 0 2 and 3 0 minus 4. So it is a 3 by 2 matrix. It is a 3 by 2 matrix. So that is your answer. It is a 3 by 2 matrix. So you see, it's a very interesting result. We can ask that if in some gate examination it may be asked that if we define a linear transformation, if we define a linear transformation from R2 to R3, what will be the order, what will be the order of the matrix T beta? It becomes the opposite. You see, it becomes 3 cross 2. The order is 3 cross 2. Okay, next problem. It's very important problem. Acha, you try to you copy it. Copy it. Continue. Shomoy, what is your problem? Write in the chat box. Okay, so below this particular problem, you will find that one statement is written that note when T of xj Shamoy has written a question, probably we have all seen it, that he has written that if we do not consider the standard ordered basis, then the matrix will be different. Do you all agree with that? Have you understood? It is Shamoy has written perfectly. It is correct. Obviously, ordered basis are where we position is important. So obviously, if you change your ordered basis, then you are going to get your different matrices. You always work with standard ordered basis, because standard ordered basis are, yes, standard ordered basis is very important. Right? If I give you, because standard ordered basis are known. Okay, so try to do a little bit of homework. Okay, say for example, suppose I am selecting, where should I write? Okay, say another page. I'm selecting the same example. Say for example, T from P3R to P2R, and the matrix representation TFX is this transformation is chosen, and the ordered basis of P3R is selected as this. And ordered basis of that is selected as x cube, sorry, not x cube, x1 x square. Okay, this is my ordered basis now, not standard ordered basis. This is my ordered basis. Now, try to do the same thing in terms of this. Try to do the same calculation in terms of this and see what matrix you are getting. And does that matrix have any connection with the this one or not? Okay. Does these matrices, do these matrices which will be, does that matrix which will be obtained by that have any connection with this one? You can do this experimentation by yourself. Try to find it out. Okay, and if you can, if you are doing it right now, and if I am online, okay, before that, if before the class ends, if you are able to find the matrix for this type of thing, and if you are able to find any connection between the matrices, and even if you are not, write in the chat box. I also am very much eager to know it. Okay. So when Txj is written, yes, but what is the answer? I mean, what is the matrix representation? Can you write in a proper way? What will be the matrix representation for this, Shomoy? If I choose these basis elements like that, what will be the matrix element? What will be the matrix? How do the matrix look like? Tell me in a proper way, write in the chat box so that everybody can see it. Meanwhile, I am going to write something in my page. So Txj is written as a linear combination of the vectors of gamma, its coefficient give the entries of column j plus 1 of T of beta gamma. Okay, if Txj is written as a linear combination of the vectors of gamma, its coefficient give the entries of column j plus 1. Tx3, so Tx3, see, you see, what is the meaning of this? They have, what is the meaning of this? Tx3, say for example, my j is equal to 3. For example, my j is equal to 3. I am considering this case. Okay, its coefficients means 0, 0, 3. These coefficients are obtained in the expression of T beta gamma in the j plus 1, that is 3 plus 1, that is fourth column. This is a result, very important result. So you are going to get the coefficient of this vector j equal to xj, x3 in the fourth column of the matrix representation T beta gamma. That has been written. X2 is the coefficient of tx2 is obtained in the 2 j plus 1, the 2 plus 1, that is third column. Coefficient of 1 is obtained in the second column, 1 plus 1. Coefficient of 0 is obtained in the first column, that is 0 plus 1 column. So with respect to our previous example, coefficient of x to the power 0 is obtained in 0 plus 1, that is first column. X1 is obtained in 1 plus 1, that is 2 column. X2 is obtained in 2 plus 1, that is 3 column, third column, first, second, and third. And x cube is obtained in 3 plus 1, that is fourth column. So Shomoy has already got his matrix. With respect to this ordered basis, he has got the matrix as 0, 1, 0, 0, 0, 0, 2, 0, 0, and 0, 0, 3. That is the matrix. 1020. What is that? Abhipriya Ghosh has written something else. Uh, when we differentiate x square from ordered basis P3R, we get twice x. But how can we write it in terms of x cube? How can we write twice x in terms of x cube? 1 and x square. Why should I write twice x in terms of 1? Something you are missing something. I am going to write when I'm selecting x square, then if I'm selecting suppose tx square, I'm writing tx square. What is tx square? Tx square equal to ddx of x square, which is twice x, and twice x will be written in terms of these items. So I can write it as 2 into 1 plus 0 into 2 into x plus 0 into 1 plus 0 into x square. If I choose tx, Shomoy has written correctly. What you are saying, I'm not getting your point. You are missing something, Abhipriya. You are missing something. So you just look at this. I want to apply this linear transformation on each of these elements, and the item which will be obtained can be expressed in terms of x1 and x square. Okay. Mute yourself, Nihal. Nihal Babu, mute yourself. Okay. Now this is the matrix what that the student has got, and what was our matrix? Our matrix was 0 1 0 0. Let us write. This is the matrix of the student, and what the teacher has got. Teacher has got 0 1 0 0 and 0 0 2 0 and 0 0 0 3. Now, okay, so this is my matrix capital A, this is my matrix capital B. Now, if I suppose this is my row 1, this is my row 2, this is my row 3. So if I interchange R1 and R2, if I interchange R1 and R2 in capital A, what do I get? I get 0, I get what? Let us check it. I get 1 0 0 0 0 0 2 0 0 0 0 3. And if I interchange in this matrix, suppose this is my new A, this is my A new. Now in A new, if I interchange C1 and C2, column 1 and column 2, we get 0 0 0 1 0 0 0 2 0 0 0 3, which is my matrix B. Which is my matrix B? Shamoy. This is my matrix B. So from your matrix, I have got another my matrix, by which? By elementary row and column operation. By elementary row and column operation. And question is, can we do such elementary row and column operation? Yes, it is, because after the examination we are going to discuss the chapter chapter 3, whose name is Elementary Matrix Operations and System of Linear Equations. So in advance, it's a very good experimentation in the class. Okay, very active participation of the student. I'm happy to see these two matrices, capital A and capital B. Capital A and capital B, these two matrices, matrix capital A and matrix capital B, they are not same, because element wise they are not same. Element wise they are not same. But the thing is that we will check, we'll see it in chapter 3. We'll see it in chapter 3. If by elementary row and column operation, if we can bring one matrix from the other, then characteristically the matrices are equivalent. Very important result. So have you got, Shomoy? How did you like this experimentation? Understood? Liked it? Yes, sir. Okay. So you see that I was discussing the matrix representation of the linear transformation, and we have got to, you and me together have performed an experiment. So what is our joint conclusion in this short research work? Our joint conclusion, let us write this research work conclusion. Research work joint conclusion is, if we select different ordered bases for vector spaces V and W, the matrices T, beta, gamma, where beta and gamma are bases, ordered bases, the matrices T, beta, gamma obtained for each case will be not equal, equivalent. They are characteristically, they will be same. So this is very important observation. If Shamoy wouldn't have asked me this question in the chat box, I wouldn't have discussed it. This was not in my planning. So since the student has asked, so I liked it very much. I didn't think that I would be able to discuss this in the class. Okay, I didn't think that I would get chance to discuss this thing today in the class. So healthy questions in the classroom, active participation of the students all in the classroom always yield good results. Okay, so always try to participate and indulge in healthy discussion in every subject, not only in mathematics. And with this last definition, I'm going to, someone has written the, okay, and now of the take help from them. Last page. Who wants last page? This one? Oh no, this one you want. Okay, so the definition, last definition I'm going to write. This definition is Very important definition. Let capital T is a linear transformation from V to W, and U is another linear transformation from V to W. Be arbitrary functions. Be arbitrary functions. Oh, they are saying that they are arbitrary functions, not linear transformations. Arbitrary functions where and V and W are vector spaces over F, and let A belonging to F, we define T plus U colon V to W. We are defining a mapping T plus U colon V to W as, we are defining a mapping T colon as this: T plus U of X is equal to Tx plus Ux. Okay, for all X belonging to V, and AT, another mapping we are defining AT from V to W by AT of X is equal to ATX. Okay, for all X belonging to V. Now this definition, I mean, it can be shown that this transformations T plus U and AT, these transformations become a linear transformation. With this, I'm actually going to conclude my today's session. What I have, why have I shown this definition to you? Let me stop the share and let me show something to you from the one of the pages of the book. So then the thing will be clear to you. Why am I showing this to you? It's because in the syllabus, you see, what is the status of the syllabus? What is the status of the syllabus? Let us check. So we have done vector space, linear dependence, independence, basis, dimension, linear transformation, range and kernel of linear map, rank and nullity, rank nullity theorem, matrix associated with a linear map, but we have not done the composition of linear transformation. Composition of linear maps have not been done. So when we consider two matrices, two transformations, T from V to W, U from V to W, in the next section, that is in section 2.3, you are going to see that we are going to compose a new mapping out of these two. So this is the premise. The definition which I've written is the premise. Definition I'm just copying from the book. You are going to get it. Okay, see, I'm showing you. This is the page of the definition I'm considering. Where is it? Okay, just a minute. I have written this definition. Okay, so this is the premise of this part, composition of linear mapping. And once it is clear, the inverse of linear transformation will be clear to you. With this particular section can be successfully finished. Okay, so I'm stopping over here. Best of luck for your upcoming examination and study properly. That much I can say. Bye for now. See you in next week. And on Sunday, there is examination. Time will be again at 6 p.m. tentatively at 6 p.m. So best of luck once again to all of you.